Swayam Prabha. Digital India. Educated India.
So now we'll just make a few things formal about this matrix. Here's a proposition. If rho represents a mixed state, then trace of rho is 1, rho is positive semi-definite and Hermitian. Okay, so recall what positive semi-definite means. Who can remind me what positive semi-definite means?
It has eigenvalues greater than or equal to 0.
Yeah, that is correct. The what he said is that the eigenvalues are non-negative. That is correct. But the definition is that for all x, this should hold. Okay. And Hermitian, of course, is that the matrix is equal to its complex conjugate. Okay, so now let us prove this. First, let us just consider a pure state. So, let us consider a pure state psi, which is summation aii. Okay. Now, what is the trace of its associated matrix? So, the associated matrix first of all is just ket bra psi psi, right, ket bra psi. So, this is because this is just a pure state, right. So, there is no summation over pi's. So, what is the trace of this? Can anyone quickly tell me what will be the trace of this matrix? Exactly, very good. So, it will just be summation ai squared, right? Mod, that is right, sorry. So, it will just be this, and this is obviously equal to 1, right. So, now if I have a mixed state, okay, then how will the trace look? So, if I consider a mixed state, okay, so I want to now look at the trace of summation over I, yeah, pi, keep doing this wrong, psi I, yeah, okay. So, this is equal to does everyone agree? Right. And now this we computed that for a pure state the trace is simply 1, right. So, then I am just going to end up with summation pi which is also equal to 1, right, because these are just probabilities. So, we argued that the trace will be 1. Now, we need to argue about we need to argue that it is positive semi-definite and Hermitian, right. So, the Hermitian part I think I will just leave as an exercise, is that fine? Okay. because it's just you just have to do this conjugate transpose and verify, and of course it's going to work, right. So let's just do this as an exercise. Okay, and now for PSD, so note that for any V, V rho V is the probability that you observe V, right, and this is obviously greater than equal to 0. Therefore, rho is a positive semi-definite matrix. So now we are going to collect these properties and give it a name. Okay. So we say that a matrix rho is a density matrix if and only if trace of rho is 1 and rho is positive semi-definite and Hermitian. So what did we show? We showed that the matrix that represents any mixed state satisfies these properties, therefore it is a density matrix. Okay. So if a matrix satisfies these properties, we call it a density matrix, and we showed that the matrix representing a mixed state does satisfy these properties. Yeah. So this is a density matrix. Turns out that the other direction also holds. So not only is it that a mixed state corresponds to a density matrix also corresponds to a mixed state. Okay. So let us just write that. If rho is a density matrix, it corresponds to a mixed state. And there is a very simple way to see this. Okay. So since our density matrix has such nice properties associated with it, right, we will just use that to build a mixed state. Okay. So since our matrix rho is Hermitian, we can write it as summation of lambda I Vi, ket bra Vi. This is how, this is by the spectral theorem for Hermitian matrices. If you have not seen this, do not worry about it. Okay, so then just believe me that you can write it like that. These lambda i's are the real eigenvalues. Okay, and the Vi's, they form an orthonormal basis. Yeah. Okay. So having seen this, does anyone want to guess what is our mixed state going to be? So I need to compute, I want some probabilities, right. So I want something like this. I want something like this. Yeah. So basically you are saying that I should write this as lambda I, right, but be careful. So these are supposed to be probabilities. So I mean I need to make sure that they sum up to 1. Why is that going to hold? Very good. So, exactly, because we already showed, right, that these lambda i's, they will sum to 1, and that is because the trace is 1. So, since the trace of rho is 1, we have that summation of lambda I is 1, right, and I can write this mixed state lambda I V I. Now, this is really nice because no matter how complicated your mixed state was, like maybe you generated it in some complicated way, maybe it was generated somehow, and maybe it had some very complex representation. But the nice thing is that any mixed state which has this density matrix can be represented as this equivalent state which is really clean, right. So, that is something which will really be useful. So, any pi psi I that you started with, you may as well sort of use the representation of this lambda I V I, and this is nice because these lambda i's V i's obviously have nice properties. One last thing I want to tell you about these mixed states is this notion of a maximally mixed state. So, this is very intuitive as we go into cryptography, because it's like I want the state, like when I think of encryption, right, I want the ciphertext to reveal as little as possible about the input. So, in some sense, if I am trying to encrypt a quantum state, I would like to kind of mix it up as much as possible, so that it does not leak anything about the underlying state. We will make all of that formal, but I will just define this notion of a maximally mixed state. So, this is when all eigenvalues are identical. So, all the lambda i's are identical, right, and they sum to 1, right. So, basically lambda I would be 1 by n if there are, if I is ranging from 1 to n, then lambda I is 1 over n. So, this is the notion of a maximally mixed state. Maybe it is also worth looking at one other idea. Is this part clear so far? Yeah. So, yeah, just one nice connection with quantum algorithms that we have seen before, right. So, we looked at this hidden subgroup problem and how it generalizes all these other problems that we had talked about. I personally find that really cool. I mean, this hidden subgroup problem, it's such a neat formulation, right, and it captures so many important special cases. So, there remember we were doing this thing where we were measuring and getting a uniformly random coset, right. So, there was this group and this group G and this hidden subgroup H, just recalling the notation from before, and we were trying to find what H is, right. And remember we were doing various things like applying QFT and then measuring, and we were getting a random coset, and then we were trying to do this a few times and get some clues and recover what H is from that. So, let me just connect that with this discussion of mixed states. Okay. So, in quantum algorithms, or quantum algorithms and density matrix, let us say. Okay, so, in the hidden subgroup problem, for group G, if our function f hides some subgroup H, then our algorithm outputs a uniformly random coset right. If you remember GH, which is 1 over root H summation over all of H, GH, right. And each coset GH is output with probability 1 over G. So, the density matrix representing the mixed state okay. So, yeah, so this just connects back what we were doing before to this mixed state, okay. So, it is just another tool that we get to think about these algorithms. Okay, so this is all that I wanted to say for mixed states.